Okay, shall we start? So welcome everyone. My name is Florian. I'm one of the organizers of the Flatland Challenge, and I'm very happy to see so many of you with us tonight. So this town hall will have two separate parts. First, we will see talks from organizers and from some of the top participants, some of the top teams. And then we will have a more open discussion. We will open the floor, and everyone will be able to ask questions to participants, to organizers, and basically it will be a free-flowing discussion. So before going further, I want to thank our partners and sponsor for their collaboration. So we are working with SBB, which is a national railway company of Switzerland, Deutsche Bahn, and the SNCF, which are the railway companies of Germany and France, respectively. So I will first make a quick overview of the different talks we will have now. I will start with a very first overview of what is Flatland, what is AI crowd, and do a 5-minute demonstration of how you can make a submission, basically, for people who didn't take part in this competition. Then we will see a talk from Christian, who will introduce some of the baselines that we've developed for this competition based on RLlib. Then Nilabha will introduce the imitation learning baselines. Then Jeremy will talk about more advanced approaches, for example, approaches using graph, differentiable conflicts. And following that, Shivam will introduce the web-based tools that he developed, which allows participants to visualize the behavior of their agents. And after that, we will hear presentation from 3 of the top teams. So Annual Driver, the winner of the OR track, on team JBR HSE, winner on the RL track, on the runner-up on the RL track, team ai-team-flatland. So to put a bit this talk in context, there are actually 3 different events happening basically yesterday on tonight around Flatland on NeurIPS. So yesterday was a deep RL presentation. So this already happened, and the recording is already publicly available on SlideShare. So what we're doing right now is a town hall. So it's recorded. So we are all being recorded as of right now. And the idea is that this recording will also be made public afterward. And then later tonight, from 3 p.m. to 4 p.m. Vancouver time, there will be the NeurIPS competition talks, which will include some live part and some pre-recorded parts with talks, other talks basically than those that will be introduced now. To see it live, you need a NeurIPS ticket, but then the recording will be made available publicly afterward. So yeah, here are some house rules for this town hall. So as you have noticed, you are muted by default, and you cannot unmute yourself. So if you want to ask a question, if it's during the talks, you can write in the chat. Most of the organizers and the participants are with us right now, so they will be able to answer your question live. Or during the open floor part, you can click on the raise hand from Zoom, and then we can unmute you on the yes, and then we can talk. Okay, so let's get started. So I will start, as I said, with a very quick introduction to Flatland, basically a Flatland crash course for people who didn't take part. So what is Flatland? It's multi-agent reinforcement learning on trains. And so yeah, as I said, we are doing this in collaboration with national railway companies from Switzerland, Germany, and France. And to take a concrete example, here is, yes, it loads, a sample of a railway network, which is the type of network that we consider. This one is rather small. And you can see some trains moving around. And so the goal is to bring all the trains from their starting point to their destination as fast as possible. And so you have all the problems that you can imagine, that you need to find the shortest path, but that then you may have conflicts, since there can be only one train at one point at one time. And so this is the gift of the competition. And we've been working on this for the past 2 years. This is actually the second competition that we organize around Flatland. And here is the team of researchers that collaborate on this. So as you can see, there are people from all around the world and from both academia and from the industry. So in this competition, the constraints were as follow. In the final round, participants had to solve as many environments as possible within 8 hours time slot. And the environments are initially small, such as this one, but they grow progressively in size. And the idea is that this allows us to measure how well submissions scale. You can see it's getting increasingly larger. And with the larger side, okay, the complexity increases, the number of agents is also increasing, which makes the problem harder and harder. And so the constraint was you need to solve as many as you can in 8 hours, but also after each batch of 10 environments, the average number of trains that you manage to reach from their starting point to their destination needs to be at least 25%. This is to save computation time if there is a solution which cannot scale to large environments. This way, it will be stopped before the 8 hours are elapsed. So that so that means that for submission to score well, it should come up both with efficient routes for the trains. This way, the execution of the episode is fast enough, and so you can do more episodes during 8 hours. But also the computation time, so the time it takes to figure out what is the next step to perform, needs to be fast as well, because you have limited time, and so if your submission is too slow, you're also penalized for that. Okay, so this challenge was organized on our website, so on AI Crowd. It's a machine learning competition platform. And actually, this year we had 3 NeurIPS competition organized on AI Crowd. So MineRL, which is reinforcement learning in Minecraft, ProcGen, which tests generalizability in games which basically look like Atari games, but which are generated procedurally, and of course Flatland. And one thing that is a bit unique about AI Crowd, that submissions are made from a repository. So this gives a lot of freedom to participants. Most participants use Python typically, but that means that if you want to implement your code using C or C++, something that some participants do in the Flatland challenges, you are free to do so. So you submit a repository like that. On the evaluator side, it's built into a Docker container, and then it's evaluated. But this build step is handled automatically, so you don't need to know Docker to take part. It's handled more or less transparently. So if we go step by step through the process, what you would do is start with a starter kit typically. So this is the starter kit for this edition of the competition. You would just clone it locally, and then set up the Conda environment to run it on your machine. And actually, the starter kit that we provided in this competition is itself a baseline. So you can directly train it on your machine and submit a trained checkpoint. And we also integrated it, so it's logging metrics. You can view these metrics in TensorBoard, but if you want, you can also use weights and biases service. If you have it installed, it will automatically use that, which means that already with this starter kit, you are able to tweak the parameters and to see how the solution performs. So the point is that new participants can just hop in and already start experimenting different ideas. So here are the parameters. The code base is basically DQN algorithm, and you can tweak typical parameters. the epsilon decay, the hidden size, and this kind of things. And then here is how you would push your submission. So it's based on a Git repository. So you add AI crowd as a remote. You make a tag for each submission, and then you push it, and this will trigger an evaluation. So here is the feedback you get. So it's actually at the end of an evaluation, but it completes progressively. And so you see here the evaluation was successful. You have the different final metrics displayed here. And yeah, okay, so here you can see your scores. And this is usually the process. So you would change parameters, you train the solution, you push it, it's evaluated, so it takes up to 8 hours, and then it arrives in the leaderboard with your score. Something we also integrated in the starter kit is you may want to test various hyperparameters to find which are the best one. And for here again, we integrated with the weights and biases. So you are able to define basically the list of the parameters, like the range you want to check, to let it train maybe overnight, and then it generates this kind of feedback. So you can see here I was tweaking 4 different parameters automatically: buffer size, hidden size, and I can see what scores it gave to my solution. And all of this can be done directly in Colab. So you don't need a GPU to run it. In this challenge in general, you don't need to use GPUs, because you use typically smaller networks, and it's not based on images. So yeah, you can go pretty far without GPU. And you can do all of this on Colab. There is a full notebook which integrates this starter kit. So you can just let it run for 4 hours, and it will train a checkpoint that you can submit to the leaderboard. Okay, so that was it for the introduction to AI crowd and the Flatland challenge. Now, if you want to work on more advanced solutions, there are multiple ways. Either you can tweak the starter kit, add, I don't know, maybe prioritize experience replay or something like that. Or you can, of course, create a solution from scratch and submit it. But something else we provided in this edition are baselines, so more complete baselines than what is in the starter kit, which are based on the RLlib framework. And I will let Christian talk more on this topic.
Hi everyone, my name is Christian Scheller, and in the following minutes I will give you a brief introduction of the Flatland reinforcement learning baselines. To start off, I want to highlight that these baselines were developed by a diverse team of contributors across multiple nations and organizations. The basic idea behind these baselines are to show that with off-the-shelf reinforcement learning algorithms, we are able to learn meaningful agents in the Flatland environment. And furthermore, we also want to give participants of the Flatland Challenge a starting point for their approaches. The baselines are implemented on the RLlib framework, which itself is part of the RAID project. RLlib includes a variety of already implemented reinforcement learning algorithms and provides a well-founded basic structure for our baselines. In Flatland, all agents share the same task of reaching their goal while avoiding conflicts, and doing so in as short time as possible. Therefore, we share the same policy across all agents in the environment. Now, at each step, each agent queries this shared policy with its own observation to get the next action. For the observation, we evaluate different approaches like global observations, local tree search observations, or observations that show potential conflicts. Our main focus hereby lies on the local tree search observation, which turned out to be simple but powerful. We represent policies with deep neural networks. These networks take the agent's observation as inputs and either directly output a policy distribution over actions, from which then an action can be sampled, or the Q values for all actions and the given observation, from which a policy can be derived directly. For our baselines, we evaluated two different reinforcement learning algorithms. The first one is proximal policy optimization, or short PPO, an on-policy gradient algorithm. And the second one is Apex-TQN, a distributed off-policy value-based reinforcement learning algorithm that utilizes experience replay. We choose them to cover both policy and value-based reinforcement learning algorithms, as well as on and off-policy learners. In the following, we'll look at how we extended these algorithms to address Flatland-specific problems. In Flatland, agents need to cooperate. To address this, we implement a centralized critic approach, where a shared critic receives the combined observation of all agents to evaluate the value of the current state. This more holistic view of the situation helps the critic to better approximate the current state value and ultimately results in more accurate updates. This critic is implemented as proposed by Iqbal and Shah in the form of a centralized actor attention critic. As such, the set of all agents' observations is embedded with a transformer network and further processed by a fully connected network. This results in an advantage estimation, which then is used in the PPO update to the learner policy. Frame skipping and action masking can be seen as two tricks based on prior knowledge of the Flatland environment to ease learning of reinforcement learning agents. Frame skipping is based on the observation that only on and next to crossings, agents can make meaningful decisions. On straights and normal curve, the best for an agent is to always move forward, if not blocked by another agent. We implement this by skipping all agents that are not on decision cells and let them move forward automatically. On the left hand, you can see an illustration of this, where the resulting decision points or decision cells are highlighted. Action masking, on the other hand, is based on the fact that always only a subset of all actions is available to the agent. For example, the basic action space includes no-op, which means stick to what you're doing, move left, forward and right, and stop. Now, if the agent finds itself in a straight, the only two meaningful actions are either moving forward or stopping. We implement action masking by simply masking out all invalid actions. In our experiments, we found that the stock global observations do not perform well, even on comparably small environments. Global density map is an observation modification that is motivated by improving the agent's performance on exactly these global observations. As such, we assume that all agents follow the shortest path to their goal. We then augment the global observation with a density map of how much traffic is expected on all routes, given that the agents follow the shortest path. The intuition is that agents, given such observation, can better decide on when to deviate from the shortest path to avoid conflicts. In the shown plot, we visualize this observation where we can see the predicted density. Hereby, red means high density and blue means low density. The same goes for a much larger environment. Here you see a 100 by 100 grid, where on the left the normal global observations is shown, and on the right we can see the density map. Now, we also evaluated our baselines on randomly generated 25 by 25 sparse grid environments, where we trained all agents on a total of 50 million frames. Afterwards, we evaluated them on a held out set of evaluation instances for a total of 50 episodes. The results show that with PPO and Apex-TQN agents, we were able to learn meaningful policies beyond random policies or such that follow simple heuristics like shortest path. Our results also highlight the generalization challenge that Flatland agents face on randomly generated test environments, which is indicated by the remarkable gap between training and testing performance. More details you can find in our paper, which is on arXiv. Now, for further information and access to the codebase, we have the following resources available to you. In our paper on Flatland RL, we introduce the Flatland challenge and describe our baselines and their results. Our public repository on GitLab contains the implementation and basic instructions of the baselines. And there's also a baseline subsection as part of the official Flatland documentation. Now I want to thank you all for your attention, and please don't hesitate to contact us on Discord.
Okay. Now we will see additional baselines also based on RLlib, but using imitation learning.
Okay, today we will be discussing about imitation learning in the context of Flatland. So the first question is, why imitation learning? Now, we know that Flatland is a challenging environment because not only agents have to learn to navigate to the target, but they also have to deal with conflicts with other agents, and the environment rewards are sparse and delayed. The actions are also not directly attributable to the rewards. Now, on the other hand, operation research solutions have done really well. They are rule-based and they follow planning approaches. And the idea of imitation learning is to use these operation research solutions as experts and try to learn from them. And this is why we think imitation learning has a good benefit in using in the context of Flatland. Now, moving on, what are the different approaches to imitation learning? So one is a pure imitation learning, and the other one is you mix imitation learning with reinforcement learning. Now the aim of using this two-step process is to see how much we can improve firstly by just using these expert actions, and then the idea after that is to get better at that. So just go beyond the expert and then further improve it. And that's why we also use a mixed or a hybrid learning. Now, coming to the next part, how do we include the imitation learning? Imitation learning we use by running these expert actions in a separate offline process and storing these expert experiences generated out of them. And then the other approach is basically to generate these expert actions on the fly as the simulations are being run and the training is performed. So fortunately, in the previous year, the competition of Flatland was held as part of the AMLD track also, and the two winners of the last year's competition were Operation Research Solutions, and we utilized them for the replacement as an expert. Now moving on, there are two algorithms in reinforcement learning. One is on policy and one is off policy. So we would like to sort of use both of these different kinds of algorithms with imitation learning. So in the case of on policy algorithm, we use the Marvel algorithm, which comes inbuilt in RLib. And then the other approach that we use is we do imitation learning and PPO and combine it. So that's how we approach the on policy approach. And then for the off policy, which is also more natural, we use the stored experiences and then give them to the Apex algorithm as part of the replay buffer. So, and then the replay buffer can also have a pre-decided ratio of expert and simulation samples. Now the trick is that you have these expert and simulation samples, but then that also means we need to combine the loss functions. So how do we do that? And one of the best approaches to do that is shown in the paper DQFT, or Deep Q Learning from Demonstrations. The key advantage of DQFT is that the idea of it is to improve beyond the expert. And this is something that we also care about a lot, because as we know, operation research solutions may not scale as well. And the central idea of how this DQFT works is this supervised margin classification loss, which is added on top of the typical DQN loss that is seen. And how it works is given also in the formula in the slide. And as you can see, that the form of this function is similar to the DQN function, except that it is in a supervised margin setting, and where you have this expert action and you have this model predicted action, and then that is the margin loss. If both are equal, then the value is 0, so there is no loss. But if the value is not equal to 0, then you have a fixed value of 0.8. The value of 0.8 is what is also shown in the paper. Now moving on, if you see that how do we implement this imitation learning for Flatland, right? So what we said earlier is we run this in an offline process and use the stored experiences, but this also has a problem. The problem is it's not scalable, and typically imitation learning also require a lot of expert samples. And the other thing is you might have these expert samples stored for a 5x5 grid environment or very small environment, but they may not work when you're training in a large environment setup. So what we did is we came up with an approach where we would run these expert actions on the fly, and then this we would integrate inside RLib. And we would have, again, you would have a pure imitation learning version of it and a mixed and hybrid imitation learning with RLib. So how we do that is, in the case of pure imitation learning, it is like behavioral cloning, where you try to match the actions of the model with the expert actions, and you use a simple log loss function to train it. Now the next step is using the IL. For that, what we do is we run episodes alternating between the pure IL approach that I just explained and a PPO approach, which both these approaches basically update the shared set of weights. Now the probability of running a pure IL approach is configurable. We set it to 50%, and it's from a binomial distribution, so they have an equal chance of running an episode. Of course, this can be tuned, and the idea of this has been taken from the well-known paper Primal, which is a multi-agent pathfinding framework. Now, what do we see as the results, right? So when we ran these against the Flatland environments, we observed, first we looked at what are the learnings that we can get just by using these expert actions without getting any RL into it. And the off-policy apex, when we used just expert samples, didn't perform as much. It performed only 23%. The Marvel, which is a much better suited algorithm because it does some intelligent sampling and important sampling, can make a better use of these expert experiences, and it goes up to 72% on the test set. While the pure vanilla imitation learning, which was through earlier mentioned the behavioral cloning approach where we train using a log loss, gave a much better test completion rate of 80%. Now, what happens when we add these imitation learning with the reinforcement learning? So for example, off policy apex, we mixed it with 25% experiences with 75% from the simulation. And the important thing to note is we combine the losses using this DQFT loss function that we explained in the previous slides. And we saw a significant boost in performance. Earlier, just with expert experiences, we saw 23%. Now it increased to 86% on the test set. Likewise, when we looked at the behavioral cloning pure imitation learning and we combined that with the PPO, the results took a slightly less mean completion rate of 71.5%. But we think this can be improved through tuning and the training between IL and RL, which can get quite complicated for the model to understand because it uses the same weights for both IL and RL, and they can have different directions. So I think if we get a bit better balance, we can get better results. So this is the presentation. Thank you.
All right. Yeah, sorry about the spam, like a rogue agent joined the chat. We will continue with approaches from Jeremy.
Hi, my name.
Here we go.
Hi, my name's Jeremy Watson. I've been working with AI Crowd on the Flatland competitions for the last couple of years, and what I've got today is a presentation on some of the ideas that we're hoping to implement for next year. So what we have is, so this one, it's started as a kind of as an attempt at as a Flatland submission, and it's a sort of graph and path front end to Flatland. We've got a sort of a directed graph representation for a Flatland environment, and there is also talk of a graph version of the main Flatland environment. So it's a possible precursor to that. It uses something called like an occupation table from OR, or also think of it as a staircase diagram, which is the occupation of resources through time. This thing supports the idea of a superposition of alternative paths for path planning, and as part of that, it gives us a way to detect conflicts and deadlocks in a plan with a sort of a linear algebra approach. This sort of conflict measure that it has is differentiable with respect to the sort of path preferences, and that allows you to then use simple gradient descent to resolve a lot of the deadlocks and conflicts in a plan. This thing has been implemented this as a separate GIM environment, so sort of separate to the Flatland GIM environment as it exists at the moment, where it has a kind of a special observation, which is where different conflicts are presented to the RL agent to resolve, and the actions from the agent will are to sort of modify or create paths in the plan, and the reward is then a kind of the improvement in the conflict measure. This thing shows a certain amount of emergent behaviour. It's a bit of a strong claim, but you know, without programming in behaviour, by just providing the right measure for the conflicts and by differentiating it using gradient descent, we get a solution. And as a sort of side effect of writing this thing in PyTorch, it runs on the GPU. Not yet, but it will. So the motivation for this has been that, as you'll have seen, that we've had kind of very good performances from OR solutions than the sort of, at least our RL baselines. The OR methods kind of have access to, they look at lots of path combinations, or at least we assume they do. We're not experts on OR. And the RL observations are kind of limited. They just kind of looking at, okay, they can see the map, they can see where other agents are at the moment. Possibly they're looking at what's another agent's shortest path. That doesn't really, or at least what we've seen so far, doesn't really have a view of what the various alternatives are. And so my conjecture here is that RL is effectively flying blind in not being able to see the lots of different path options that other agents have. Okay, so the graph representation, if you naive graph representation doesn't capture the semantics of the junctions. So kind of a year ago we wrote this directed graph representation for a Flatland, where it also has these different types of nodes to represent the direction of an agent. And so there's a sort of a junction in detail, how the various directed edges are connected together. And by using that directed graph approach, we can now use standard algorithms to pull out the shortest path or the k shortest paths from libraries like Network X, which is the one that we've been using. Okay, so as I mentioned earlier, this thing kind of supports the idea of lots of alternative paths. So as a simple approach to generating these alternative paths, we just you take the shortest path, and then for every junction that you pass, for every diverging junction that you pass, you take that alternative course and follow the shortest path from there. As an aside, we don't really model the recombination of paths. They're basically it's just a bunch of paths. It doesn't really it has no conception of how these paths diverge or converge back together. Okay, so back to the idea of conflicts. We've introduced these sort of direction nodes, and that kind of makes it slightly more complicated to detect conflicts, because if two agents are heading in different directions, they're actually on different nodes, even though they're in the same flatland cell. So we just have to have a bit of logic to tie those direction nodes to the, I'm calling them the grid nodes, the red ones. Okay, here's this example of this thing called a staircase diagram. Looks like a flag, where we've kind of got the resources or the flatland cells on the y-axis, and the time steps on the x-axis. Agent 0 starts in the top left here and heads down to the bottom right, and meanwhile we've got Agent 1 coming in the opposite direction and kind of colliding in the middle. Okay, so now clearly we've got an alternative path here, or the possibility of an alternative path, which is this little siding here, this staircase diagram, can look a little bit confusing once you start introducing the alternative paths in there. But see, here's Agent 0. It can carry on in a straight line, or it can head around the siding and then carry on a few steps later, a few steps behind where it would be. Similarly with Agent 1, it's heading up here, and then it could take the diversion and then carry on up there. But obviously the way that we've constructed this little test environment here, that doesn't solve the environment. You've still got another conflict there. I've mentioned a conflict measure and the sort of the occupation table. So this coloured one here is like the sort of occupation table, which just records the sort of presence or the probability of the presence of an agent in each cell versus time step. This over here is the kind of conflict measure. So we've got a bit of logic coming up that detects these two conflicts. And then the overall kind of global conflict measure just kind of sums all of these, so you kind of get a number for the plan. Okay, so if we add the pause in there for sort of Agent 0, then the staircase diagram starts to look like this. So here's the pause, and here are the sort of various alternative paths, and they're shown here as a sort of lighter colour, because in this example, the probabilities have sort of been adjusted by the gradient descent to sort of promote a version of a combination of the paths that has a lower conflict measure. So just to kind of bang on a bit more about the alternative paths, think of it as like Schrodinger's path. Each agent has a superposition of possible paths, and we've got a probability vector, or a preference vector, which we use softmax to turn into probabilities. Then in order to select the paths, it's like, well, it's like the collapse of the wave function, if you bear with me. And that's kind of this sort of in a way, that's the sort of the fundamental aspect of what we've written here. I'll kind of go on to explain how do we tell the difference between different paths from the same agent versus different agents occupying the same cell. So in order to, what we don't want to register conflicts if two potential paths are really associated with the same agent. So we just do this thing with a bit of linear algebra or a quadratic form. To just multiply the probability of one agent with the probability of all the other agents in each cell and at each time step. So you end up with these sort of patterns like this. So you've got agent A, agent B, agent C. So you've got AB plus AC plus AD plus BC plus BD plus CD. And so no matter what, if A is the only agent in the cell, then the number is always going to be 0, because A is only multiplied by the probability of the other agents. So if you get, a chance of agent A and a chance of agent B, then you start to get a non-zero number, which represents the conflict. There's a bit of math sort of notation here if you'd like to pick through it later. Just to kind of mention here that we've got this kind of upper triangular matrix that we use to calculate the conflict number here, to sort of reproduce that quadratic form that was on the previous page. Okay, and obviously this thing is differentiable, so we can use gradient descent and quickly just find a sort of local minimum. Just a few notes there about some of the details and some possible alternatives. So, okay, now we're detecting conflicts. We haven't really talked about whether those conflicts are head-on kind of deadlocks or sort of same direction conflicts where one agent has stopped in front of another. So we use an extra dimension to model direction here. And even that isn't quite enough because there's a bit of explanation here about, like, if the agents are sort of 2 steps apart and then they're 0 steps apart as they move together, and then they hop over each other or they sort of would hop over each other if they didn't collide. That has to be modelled in one way, and then we have a separate way of modelling it if they're an odd number of steps apart. So it's slightly unfortunate, and if anybody can think of a better way of doing this, please let me know. So all in all, we've got these 3 types of conflict. We've got sort of a regular conflict, or sort of same direction conflict, and then 2 types of deadlock. And we just we have to kind of create 3 occupation tables for all of these, and for the conflict measure, we just add them all together, probably with a weighting. So here's another illustration of the same thing. So each agent, we've got 2 agents here, agent 1 and agent 2. We've got lots of paths, which are sort of represented here as sort of paths through the occupation table. Each one has a preference. So we've got like a preference vector, or this is more like the probability vector here because it adds up to 1. So we kind of sum together all of these paths, or sum product them with the probabilities. So then we get a kind of a weighted occupation table, sort of weighted according to the probability of each path. We get that for each agent, and then we sort of pass this through the quadratic form logic to get the sort of conflict table at the bottom, where here we've just got like a couple of conflicts from those that we saw earlier. And as I say, this whole thing unfortunately has to be replicated 3 times. Once with simple cells, once with the sort of UV edge representing the direction of the agent, and then again the sort of, I'm calling it PS, of the sort of the cell before and the cell after in a path, which then sort of captures the other type of deadlock. There's some more notation there. I'm trying to be a bit more precise. Okay, so now pausing. So clearly, we need some sort of way of introducing pausers into this, and we have a sort of an interim solution. Prior to sort of introducing this, prior to sort of using an RL agent, we were able to just generate a bunch of not exactly random pauses, but just create a lot of alternative paths, each one with kind of 1 pause in it. So it's just a sort of heuristic, really, just like looking at each junction and creating a path, or creating a copy of the path that pauses just before that junction, and then running the gradient descent on the whole of that. And that actually kind of works reasonably well, from competitive with the RL offerings already, without really doing anything very clever. Obviously, there's a bit of a scaling issue with this, because you've got your agents, and then for each agent you have alternative paths, and then for each alternative path you've got alternative paused versions of that same path. So 50 agents quickly turns into 5,000 paths. Now we've programmed this in a certain way so that it doesn't eat up a lot of memory. We tested it up to around sort of 20,000 paths, and it's only using a handful of gigabytes of memory on the CPU anyway. It uses this thing called index put in PyTorch, but we still need a smarter way to introduce the pausers and possibly also even the alternative paths. So rather than creating everything up front at the beginning and then gradient descenting to sort of optimize it, the idea is that we create less at the beginning and just use the RL to gradually add things in as they're needed. Okay, so that's basically what I just said. So the observation, okay, we're moving on to the RL part, and the observation that we've got so far is a sort of intersection, as in the set intersection of two paths. And when I say intersection, I don't mean like a junction or an American highway intersection, I mean a set intersection. So here's our example again. And so the observation is on the right, and basically you can see that the yellow squares mean that the path, each respective path for agent 0 and agent 1 are in the intersection of the two paths. And this is ordered by time steps, so in fact the spatial order is kind of reversed for agent 1. And so you can see that agent 0 is they both start in the intersection. Agent 0 leaves the intersection first as it goes round the siding, and then goes back into the intersection, and sort of similarly but opposite for agent 1. Clearly the answer here is for agent 0 to pause just before the junction, and so the sort of effect of that on the observation would be to shift that yellow section there for agent 0 further along. So we did some, just kind of, we're only really sort of messing around with this in sort of prototype form here, and so there's I managed to train a simple network to reproduce that pausing behaviour, and to generate lots of examples and train the network. And it's a little bit like kind of training a network to imitate a heuristic, and the Flatland competition takes a sort of dim view of this, so it will probably not be admissible, but it's just an example to show that it's possible to reproduce this behaviour by training a simple neural network. This was just like an NLP. Okay, so there's a few other sort of details to the RL observation. Is it a conflict or is it a deadlock? And then is it resolved or not? Obviously you can think of different things, extra things that could be put into this observation. At the moment, we're kind of keeping the observation small, just in order to sort of to make the training easier. Okay, and then the reward is clearly where we've got this thing called the conflict measure, and the reward is going to be related to how this conflict measure improves. And there's a kind of a design decision as to whether it should be related to the local conflict. How has the action improved the local conflict that it's operating on versus the kind of global conflict measure. But there's some sort of it's kind of related to what we include in the observation. Okay, there's another point about observation sequencing, where if we at the moment did this sort of as this thing was first implemented, just presents a conflict, the RL agent provides an action on that conflict, and then the next observation is a completely different conflict. And so that way the RL agent never gets to see the effect of an action on the set of state, the piece of the sort of subset of the state that it's looking at. And so we're probably so this is it's going to break the state, action, reward, state, the next state sort of sequence. So the obvious answer is to just after it's provided an action on that observation, to give it the same observation again, but with the action, or rather the same conflict with just the action applied to it, so that it gets to see the effect of the action, and so it can start to train a value function on the observations. Okay, so the way that we're currently encoding the action is just as three scalars: which agent, when to pause, and how long to pause. And obviously we could do that different ways, using one hot vector to do something, but this is what we have at the moment. Okay, so yeah, we're hoping obviously to get some sort of emergent behaviour from this, that it should work out how to do things itself rather than us program too much in. So we're trying to do planning, but it has to work out how to do that planning itself, it being the RL agent, or the neural network combination of networks. I say keeping the observation small. It would be nice to include other information like the background. So obviously we're presenting two conflicting agents to the observation but it would be nice to have other sort of background agents included in there as well, or possibly the alternative paths which could be available to this agent. Obviously at the moment we want to kind of keep it small. And I think as well, we would need to move to a different form of, we don't want to just use fully connected networks to interpret these observations. We probably need to sort of introduce some sort of like a convolutional network, or some of the sort of sequence-based networks that will kind of look at the path, along the path, like a sort of LSTM. But for us, this, we have not yet explored this. Okay, a bit of it's kind of software structure really. You've got the Flatland environment on the right, and then this new thing which we'll call a conflict env in the middle, which is kind of doing the planning. And so the RL agent is interacting with the conflict env and refining the plan. And then once all the conflicts have been resolved in the plan, it then starts issuing that plan, or issuing actions to the underlying the true Flatland environment. And of course, it needs a mechanism in there so to when Flatland says that there's a malfunction with an agent, it needs to sort of do a little bit of replanning. But I hope that you can see already that this thing already has the mechanism for replanning. It's just like, okay, there are some new conflicts, and we just resolve them in the same way. So this isn't written yet, but I'm hoping that it doesn't seem like it should be too complicated. So this conflict env, it's implemented as a gym environment. Obviously, it's written in PyTorch. It does quite a lot of does linear algebra style operations. It's a bunch of assignments and then a bit of linear algebra. So all of this is stuff that runs quite nicely on the GPU. We've tested a few simple, small sections of the whole mechanism, as it were, and obviously we get a big speed up. Haven't yet, transform the whole sort of the whole suite into sort of GPU yet. I just kind of run small subsets of it. So some plans and intentions. Obviously, we want to try and introduce this into sort of some of the public Flatland package or packages. Obviously, we're going to explore that observation and hopefully generate some benchmarks with some standard RL agents, as we have done with the existing sort of tree view. Clearly, we'll between us and the competitors, the participants, we need to explore some different neural network models to consume this observation. There's a few references, and thank you very much for listening. That's my AI Crowd email address there, and we very much welcome anybody who would like to collaborate on next year's competition. If there is anything here you'd like to cite, then I suggest you just cite the Flatland paper, which we've just got onto archive very recently. Thank you very much.
All right. So we will now switch to the talks from the top teams. So now it's up to the participants of the teams if either I play the pre-recorded video, or so this is the same video that will be played tonight during the competition track, or alternatively you can tell me now, and if you want to explain it or explain it in a different way live, this is also fine. So I'm getting ready to start the video for an old driver. Let me know quickly if you want to click live.
Hello everybody, I'm Jiaoyang Li from University of Southern California. I'm going to represent our team and old driver to present our solution for the 2020 Flatland Challenge. Here are the team members. We have myself, Zhe Chen from National University in Australia, Yi Zheng and Shao Hongzhan from University of Southern California in the United States. We also have 4 advisors, including Daniel Haribo and Peter Starkey from National University in Australia, Han Ma from Simon Fraser University in Canada, and Sven Koenig from University of Southern California in the United States. The reason why we have team members from different countries is that we are all interested in a very exciting research topic called multi-agent pathfinding. Flatland Challenge is indeed very related to this problem. Our approach consists of 4 components. The first one is process planning, which is a popular multi-agent pathfinding algorithm. It first plans a shortest path on the map for the first agent. It then plans a shortest path for the second agent while avoiding collisions with the first agent, while avoiding collisions with the first 2 agents, and so on. Each shortest path is planned by an algorithm called safe interval path planning, and once we have planned paths for all agents, we get an initial solution. Then we improve the solution quality by large neighborhood search. In each iteration, we select a neighborhood, which is a subset of agents, and we plan the paths for them. If the new paths are better, we replace the old paths with them and repeat this procedure. We have designed 3 different ways to select neighborhoods. The first one is to select agents who have the same start station. The second one is to select agents who have passed through the same intersection. And the third one is to select the agent who have the longest path, together with the agents who block this agent. During execution, agent may encounter malfunctions. For example, this is an original plan. But if the light blue agent is delayed by the malfunction, then we will have this deadlock. We therefore use MCP to address this issue. MCP keeps the ordering of the agents to visit each location and thus guarantees deadlock free. For example, if we keep the ordering of the agent to visit this intersection, then when the light blue agent is delayed by malfunction, MCP will also delay the dark blue agent, and deadlock is addressed. However, such delays is not necessary in all cases. Here is another example. If the orange agent is delayed, MCP will also delay this green agent. But this is unnecessary because the green agent can actually reach its goal locations without waiting for the orange agent. We therefore use partial replanning to improve the solution quality. We collect the intersection that the malfunction agent is going to traverse, and we plan the paths of the agents who are going to traverse these intersections after the malfunction agent. To summarize, in our approach, we use process planning to find an initial solution. We then use large neighborhood search to improve the solution quality. During execution, we use MCP to avoid deadlocks, but we use partial replanning to replan some paths to improve the solution quality during execution. To talk about what we have learned from this competition, our group's research often focuses on multi-agent pathfinding algorithms that have guarantees. We want to guarantee that the solution we found is optimal, or at least on this suboptimal. These guarantees are nice to have, but in practice we don't need them. What we need are good quality solutions for thousands of agents, and we need these solutions fast. These insights lead us to product planning. But on the other hand, these optimal solutions are not useless. We use them to identify which part of solutions in the product planning can be improved. And this helps us to focus on small groups of related agents to improve the solution quality. And indeed, large neighborhood search and partial replanning both use this idea. And this ends my talk. Thanks for listening.
All right. Now starting the video for team JBR HSC.
Hello, I'm Alex Vichenko and I'm here to describe the approach of our team. Hello, I'm Alex Vichenko and I'm here to describe the approach of our team JBR HSC. We represent the Laboratory of Agent Systems and Reinforcement Learning of JetBrains Research, as well as the National Research University Higher School of Economics. We are based in St. Petersburg, Russia. To begin, I will tell you about how our real agent interacts with Flatland environment. In our reinforcement learning approach, we use common features that we calculated from global environment, as well as features computed from so-called tree observation, similar to the one provided by the Flatland package. For the description of observation, we refer you to the website of the competition, and for the list of features, which is quite extensive, we refer you to our source code that should be made public by the organizers. As per the training setup in terms of reinforcement learning, we introduced the following modifications. First, the agent can make actions only if it is close to an intersection, and otherwise it will simply move forward. Second, the learning episode ends for an agent that is deadlocked. The reward for our setup consisted out of 3 parts. Delta D is the shortest distance to the goal. Is succeed and is deadlocked are corresponding binary indicators. For our solution, we modified a basic PPO algorithm in following way. We encode common features and 3 features by 2 separate networks, and then combine them via a fully connected layer. We then pass the output of that layer to a communication block that generates an outgoing message vector of an agent. The incoming messages from neighbors are processed via a multi-head attention block, and together with feature vector are processed by the action block of an agent that outputs an action distribution. The critical architecture is composed in a more straightforward way. We simply use only feature vector to predict value function. After training an PPO agent, we noticed that agents are tend to deadlock if they are all allowed to move since the beginning. Considering that, we came up with an idea that agent's departure should be scheduled. In the first stage of training, we use a simple short distance first timetable to define which trains should depart and which trains should wait for departure. We then implement a Scheller network that tries to evaluate the probability of success if the train will depart at the current time. The final solution consists of both agent and Scheller networks. We would like to thank the organizers for giving us the opportunity to participate in an interesting challenge, and we would also like to thank the Higher School of Economics for giving us access to their high performance computing resources. Thank you.
All right, now the final video from participating teams, ai-team-flatland.
Hi, I'm Evgenia. I'm a data scientist at NetCetera, and I want to talk about NetCetera and our solution to the Flatland challenge. So here are some of the projects that we have been involved in the past. We have experience with healthcare industry, with manufacturing process, with face recognition, and also some challenges like the Alpha Pilot challenge. And here are all the specializations that we have experience with. We wanted to add another field here, the reinforcement learning field, and we thought that the Flatland challenge would be a perfect opportunity to do so. So here is the team behind the Flatland challenge, and here is our solution. Same as last time, we built the reinforcement learning solution on the Flatland environment, where the trains are our agents. We have positive and negative reward, and finally the model, which takes the state of the agent as an input and outputs the correct action. The first choice we need to make is how to represent the environment. The most obvious choice is to build this cell graph where each node is a cell in the map, but we can see that many cells have a degree of 2, and we can merge them into this switch graph, which means that each node is a switch and there is an edge between two nodes if there is a direct path in the map between those two switches. But we were missing another piece of information here, the direction, and the final representation of the environment in our solution was the following one, where each node is a combination of a switch and a direction, and we have a directed graph for the environment. We built upon the proposed baselines with the RL-lib module. We tried different training model environment configurations. For example, with the models, we experimented with off-policy and on-policy models. We also introduced iterative learning, where at the beginning we provided the training process with some simple environments, and then we increased the complexity. In the observation vector, we include many different things, but the most relevant turned out to be the priority, the conflict info, for example, deadlock, potential conflict, deadlock in the bigger segment, for example, until the next usable switch and so on, and also some info about the shortest path and the alternative path, which means second shortest path. Here is the reward structure. So we gave a large positive reward if an agent gets into target, a large negative reward if it gets into deadlock, and also some smaller penalization for unwanted behavior, for example, stopping on switch, not following priority, and so on. And here is the result. 88% of the agents reached the target, and we got to level 22, which means 181 agents and 20 cities. And here are the impressions of the Flatland challenge. It was really challenging at moments, but at the end really rewarding because we finally managed to do a well-behaving agent. We learned a lot, and we have also new ideas to try. At the end, I want to say thank you for an amazing and fun challenge. It has really been a pleasure, and we are looking forward to the next round. You can reach us at ai-team-flatland, etc.com. Don't hesitate to reach us with question or just get in touch. Thank you.
All right. So everyone that we've heard so far, including myself, have the goal to kind of solve this environment, solve this problem. Now for the final video, I will show what Shivam built, which is a bit of a different approach, since his goal is to visualize the problem and its solutions rather than directly trying to solve it.
Hello and welcome to this virtual presentation. My name is Shivam and I will present our work titled Adventures in Flatland, Visual Analysis of Multi-Agent Movement in Virtual Rail Networks. The work was done in collaboration with Gunter Waldner, Jeremy Watson and Fabian Beck. Multi-agent environments have unique opportunities and challenges. Addressing these challenges often involve agents to coordinate among themselves and complete their tasks. However, analyzing the collective behavior of agents in such environments is not a trivial task. Such analysis needs to consider the mechanics and details of the environment to derive relevant insights about the behavior among agents. In this work, we present a visual analytics approach to analyze the behavior of agents in a virtual multi-agent environment called Flatland. As introduced in the previous presentations, Flatland is a multi-agent environment for trains. It simulates the scheduling of trains on virtual rail networks. It provides maps with different layout of rail networks. Also, the environment supports generation of maps with different sizes. The layout and size of the generated rail network constitute towards complexity of the train scheduling techniques. Each map has some number of trains. Each train has a starting position on a track and a station as destination. Trains can randomly experience malfunctions, which restricts their movement for some time. And finally, in the current version, all trains in Flatland move at same speed. The goal of a scheduling technique is to schedule maximum number of trains to reach their destination as fast as possible. Modeling each train as an agent makes Flatland a multi-agent environment. Now let's watch a playback of train movements on a map. Here, a reinforcement learning approach was used to schedule the trains. Playbacks like these are commonly used by developers of the train scheduling technique to gain insights about their behavior. Specifically for machine learning based scheduling approaches, the playbacks are used to judge whether the agents have learned good scheduling strategies or not. However, playbacks like the one being shown here are not very efficient to say anything about the strategies exhibited by agents. It is challenging to keep track of individual agents' movement simultaneously and gain insights about the collective behavior. Simply put, the playbacks are too fast and there are too many trains to follow at the same time. For instance, in this example, based on the playback, can you derive insights about the scheduling strategies exhibited by the agents? Before designing our approach, we conducted interviews with Flatland experts to understand their information needs. We interviewed 3 experts where each interview lasted for about 30 minutes. Based on these interviews, we derived 5 specific analysis goals. The first analysis goal is about getting an overview of events and actions in the schedule of individual trains. Also, to provide important statistics, for example percentage done, the number of trains that reach the destination for an individual episode. Second analysis goal is about analyzing the utilization of resources in a rail network. This includes analyzing the usage of long rail lines connecting distant places, critical junctions in the rail network, and areas with high number of stations, and so on. Next, the experts mentioned the need to assess the efficiency of train schedules. Since this assessment needs some reference, often the actual path of the train is compared with the shortest path. This plays an important role in deciding awards when using reinforcement learning based scheduling approaches. Moving on, understanding the causes of issues, for example deadlocks, malfunctions, and bottlenecks, is a crucial step to improve a scheduling technique. Hence, the fourth analysis goal is about the ability to investigate the cause of these issues. Also, to analyze how these issues affect other trains and regions in the rail network. Finally, experts highlighted the need to explore scheduling strategies exhibited by the collective movement behavior of a group of trains. Such exploration is required to understand whether trains are collaborating by reacting to the actions taken by other trains or not. It is clear from the analysis goals that the approach should provide both spatial and temporal perspectives through the visual analysis. Based on the analysis goals, we designed a visualization approach to help analyze the train movement behavior of a scheduling technique. The approach consists of 3 linked views, providing different perspectives on the train movement data. The figure shows the full interface of the proposed approach. Let's discuss the 3 views one by one. The timeline view aims to provide an overview of individual train schedules. On top of the view, we show statistics on number of trains in the episode that needed to be scheduled, percentage of trains that reached their destination, and the number of trains based on their end status. Each row in the view represents a train, while horizontal axis shows a timeline from left to right. The trains are grouped in 3 categories according to their end status. The first group representing the trains that reached their destination, followed by those who were still on track when the episode ended, and finally those trains who are yet to be scheduled. Within each group, trains are ordered based on their starting time. For each train, we show the important events that occurred during its journey. The starting time of a train is encoded as a black ring, while movement is depicted as an orange line. Since trains mainly make route decisions at junctions, we also encode reaching a junction by a pink diamond shape. Malfunctions are represented by a cross with a tail, where the length of the tail denotes the duration of the malfunction. If trains are involved in a deadlock, they are represented by red squares in their timeline. Finally, the arrival of a train at its destination is shown by a black fill circle. Let's zoom in on the timeline of trains that are still on track. Here, we see several lines connecting the red squares at different time steps. It highlights the trains that got involved in the deadlock. Hence, it gives a clear impression of how a deadlock affects other trains during the runtime. Next, to assess the efficiency of a train's route, we calculate the length of the actual path taken and compare it with the shortest possible path length. We represent the actual and shortest path length for each train using the black and green horizontal bars. To provide a temporal overview aggregated across all trains, we include a histogram at the bottom of the timeline view. The height of each bar in the histogram represents the summed value of the selected metric aggregated across 10 time steps. Available metrics which can be selected are distance traveled, number of trains that are departing, arriving, experienced malfunctions, and number of crossed junctions. Here, we can see that in the middle of the episode, there was very little movement of trains. Next, we include a map view in our approach to provide a spatial perspective of train movement in the rail network. The stations are labeled, while each train is represented by a numbered circle. To analyze specific parts of the network in detail, the map view supports zooming and panning interactions. Movement of trains on the rail network is shown as an animation, which can be enabled through playback controls at the bottom of the view. To highlight the utilization of each rail tile, we show on demand the occupancy time as a heat map. To analyze utilization of specific resources in the network and details of train movements, it becomes important to focus on specific regions. We provide 2 modes of specifying regions of interest in the map view, which can be selected by the 2 icons at the left of the view. The first mode is a rectangular range selection through mouse drag. With this, a single cell can also be selected as a region by a left click. The second mode selects a clicked rail segment between 2 junctions. All selected regions can be cleared by clicking on the button with the red cross. For the analysis of movement between selected regions, we integrate a graph view in our approach. Positioned at the bottom right of the interface, it contains a directed node link diagram. Here, a node represents a selected region, while movement of trains between regions is represented by the links between these nodes. The size of a node indicates the number of trains that have been in the corresponding region at least once. Since a train can move between regions multiple times, the width of a link represents the number of transitions from one selected region to another. two variants of the graph are selectable. First, the aggregated graph provides an overview across all time steps. Second, the animated graph shows the same information for the current time step. For instance, the animated graph for the episode at time step 65 is shown here. The small circles on the edge between regions represent the trains in transit between the two regions. Details are available while hovering through tooltips. Now, let's watch a demo of the tool showing the implemented features and interactions. An episode can be selected from the drop-down menu at the top. Next, we define 4 regions in the map view. First region is a rail segment, while others are specific areas around the stations. As you see, the graph view is updated accordingly. The time slider can be used to look at specific time steps. The episode can be played with the playback controls below the map view. This not only moves the trains on the map view and the animated graph, but also the blue time slider on the timeline view. We integrate highlighting consistently across the views. Hovering over a train in any of the views highlights the corresponding row and circles with a yellow background in all views. For instance, here the row of train 9 was hovered in the timeline view, hence the train was also highlighted in the map and animated graph. Accordingly, hovering a region in the map or graph highlights all the trains that have visited the region. For instance, hovering over the region R1 revealed that 9 trains visited the region. Additionally, a semi-transparent gray rectangle in a row in the timeline view shows the periods spent in the region by the corresponding train. This feature is a way to connect the spatial and temporal perspectives during the analysis. Next, let's talk about some insights that can be derived through the visualization. From the overall statistics at the top, we infer that out of 42 trains, the reinforcement learning approach was able to schedule only 27 trains to their destination, with 13 trains being still on track until at the end of the episode. There were several trains that were involved in deadlocks affecting the scheduling. Furthermore, hovering over a track that was defined as region R1, from the width of semi-transparent rectangles on the timeline, we observe that except train 35, all trains who visited the track spent the same amount of time on it. On a closer look, we see that train 35 witnessed a deadlock while being on the track and did not move until the end of the episode. In addition, judging from the heat map in the map view, reinforcement learning did not utilize one of the parallel tracks at all. We do not see such issues for the operations research approach, but a more even spatial and temporal utilization of the network. In another episode, we observe a cyclic movement marked with orange line and waiting, highlighted by white gaps, in the timeline of train number 6. Defining a rail region as region R1 and hovering over it reveals repeated visits, revealing that the train is stuck in a loop. To observe the difference in utilization of parallel tracks by the reinforcement learning and operations research solution, we selected individual cells as regions inside parallel tracks. As shown here, regions R2 and R3 form the endpoints of one track, while regions R4 and R5 offer a parallel track. In the reinforcement learning solution, bidirectional links between the pair of regions in the aggregated graph show that the parallel tracks were used to operate trains from both directions. In contrast, the operations research solution used the parallel tracks only in one direction each, which can explain the much better overall performance of the operations research approach. To understand the usefulness of the proposed visual analytics approach, we conducted a user study with participants from the Flatland community having experience in operations research as well as artificial intelligence. We also invited few participants from visualization research community as well. The participants were able to use the system and report several insights. Highlighting few comments by participants, P2 liked that the tool allows to see the density of traffic over time. While many participants observed that operations research technique operates denser traffic, which makes it possible to schedule the trains in much less time than reinforcement learning solution. Another participant said that it was cool that the tool allows the combination of different selections for region definition. Also, the map view allows detailed investigation of situations like deadlocks identified from the timeline view. Going ahead, the participants suggested valuable features for inclusion in the tool that would add more value in the visual analysis. These suggestions include a better way to visualize the comparison between two or more scheduling techniques on the same map. Insights derived from the comparative analysis could further advance the research of scheduling trains in Flatland. Second, integrating the agent observations in the proposed approach could also be beneficial to understand the reasons behind actions taken by agents, which is important to further improve artificial intelligence-based solutions. While our approach has been developed for the Flatland environment, we see potential of use in related scenarios, specifically in those multi-agent environments where agents need to move around. For example, in analyzing implicit road rules in multi-agent driving, cooperation among autonomous robots in a warehouse, movement of product parts in manufacturing, among many others. With these visualization adventures in Flatland, we hope to have contributed valuable support to the community and made a step towards establishing visualization as a standard tool for analyzing complex multi-agent scenarios. I want to leave a key takeaway from this talk, that is, consider using visual analytics in multi-agent environments to debug, analyze, understand, or improve the behavior of trained agents. Finally, I want to thank Florian for patiently answering all my queries over the past few months. It really helped me to familiarize with myself with the Flatland environment. I am also indebted to the Flatland community members for participating in the interviews and the user study. Thank you so much for providing valuable feedback.
All right. So thank you to everyone who provided these talks on recordings that we have seen so far. It was very exciting to see them all. So we are right on time, quite on topic for train scheduling. We will now open the floor for any question. I've seen that some people already asked some questions in the chat. Maybe we can already repeat these questions quickly, because people may have been watching the video. So we will now. Okay, so now everyone can unmute themselves. So if you have a question, feel free to unmute yourself. Let's not raise hand. I think it's enough with 23 people. We can just handle the sound together. So Shivam, I saw that you had a few questions for the participants.
Yeah, so I had actually 3 questions and I've got some of the answers. So maybe I'll start off with the 4th question then. My question would be, while training the agents, have you ever seen any occurrences where agents learn some good strategies and are able to solve some specific use cases in the environment, but later on with the further training, they unlearned that behavior? Have you encountered this in your training?
Well, yeah, because there a problem called catastrophical forgetting that leads to forgetting some well rules that policy already learned, and it seems like it good enough, but sometimes it just have high score and then boom, low score, and well we trying to figure out how to solve it in these cases.
Great, thanks.
Yeah, maybe one thing on this topic that we really would have wanted to provide, or that we would like to provide for future competition is some kind of unit tests, right? So you could have a set of pre-configured networks that would be hand-drawn, for example, to test simple, basically from sanity check situation to make sure that the agent don't get into deadlock up to more advanced situation. And then every time you do an evaluation of your agent, you could have like a checklist saying, okay, it's able to do that, or maybe there was like what you would call a regression if it was a bug. This kind of test.
It seems like a good idea because in our research we faced some situations when agents do strange things, like just standing or standing against each other, so just moving in different way, just know that way that they should move, and it's hard to understand why they do it, because it's large multi-agent environment with a big amount of variables, and it's hard to understand what we should change in our policy and our algorithm to improve it.
So maybe a follow-up question would be, do you often kind of design some network layouts yourself to test the agents?
Nope, we just record some episodes, like just render them and look into it. What happened that prevents agent from reaching its target?
Okay, so I will ask a more general question to all participants, not only to the leading teams, but to anyone who has either taken part or played with the environment, which would be, yeah, generally, what would be what are the big pain points? What would be the improvements that you would prioritize for the next competition? No problem. Everything is perfect.
Florian, I'll just jump in to say, now the room is locked and it's just the 23 of us who are here in this room. So, I would sort of nudge everyone to even switch on their video. It would be good, also a good moment for us to see each other, all the people who have been participating, and sort of this becomes that place where all of us are coming together. Now I see people are switching on their videos. I would nudge even more people to do so. But in any case, Florian, he wanted to ask this question. Florian, go on.
Well, now it feels slightly more like we are actually at NeurIPS and we can see each other, right? Yeah. So my question was basically what would be the main problems that you had as participants, on what you would want us to focus on for the next challenge.
So for us, because we use OR methods, so it actually takes us a long time to figure out the actual detailed rule about how the agents move and what the conflicts look like. Like, for example, when we, like in round one, like it takes a long time to figure out, okay, actually the agents are not moving in a symmetric, way, like where like the collisions depend on the indices. And also, like, I think in both round one and round two, there's a, what we call a hidden like rule that once an agent commit to an action, like a move, for example, move forward action, and it got malfunction, then later when the malfunction disappear, you are not allowed to change that move, like that action, even like stop. So like that causes us some issues when we do replanning during the execution. So I mean, it will be helpful, like if next time we can like try to write this kind of rules like more explicitly, so that we can know it at the beginning instead of like playing with it and figure it out like by ourselves. Yeah.
Yeah. So this boils down to documentation mainly, right? Having a more formal definition of how the agents move. We spent a lot of time documenting the environment better on gathering. I mean, this is a distributed project where a lot of people took part along the years, and so we put a lot of effort putting all the documentation in one place and in a consistent format. But yeah, I fully agree. There are, for example, when we were working on the papers, there was some point where like I'm not 100% sure about that, and we had to go check the actual implementation, which I agree would be should be documented. What
if I can,
is that sorry?
Just if I can say something here, there's this one thing is also so some decisions cannot be reverted. So if you're on a switch, we assume like in real life, if the switch has been turned to one side, you cannot just turn it to another side again. So if you malfunction on a switch while you wanted to deviate, you cannot change your decision back after the malfunction to go straight. But I agree that the stop action should always be allowed.
Okay, I see a lot of activity around communications. So Nilabha initially asked, I'm wondering how much benefit the communication provided. Was one of the unique aspects of the solutions. Yeah, a lot of +1 in this direction. So yeah, I would also be very curious to hear more about this.
Yeah, our communication is just simply like we generate a message that we pass to another agent, and this agent considers this when generates action. We simply just allow gradients flow through this message in training stage.
But to which it can communicate with all of the trains, or how do you decide how?
No. It can communicate only with closer trains on each edge. Like we used tree observation, and for each edge we took a closer agent with and make agent communicate only with this agent.
So I'm just wondering, how do you keep the size of this communication vector constant, irrespective of the grid size?
Well, we do not. It's like just in terms of neural network, it's just like a middle features vector. So we do not need to keep a specific norm of this vector.
Okay, so each agent has that fixed size.
Yeah.
Okay.
Okay, it seems the questions might die down. The NeurIPS lunch break, it ends in about 20 minutes. So we have time until then to keep the questions going. Jeremy, I think you wanted to ask one or two more questions.
Yeah, I suppose who was it who used some attention? Did someone use an attention mechanism to pick the other agent or the alternative path? I don't know if that was it Oleg or?
I think the modified actor critic had the attention.
Yeah, I mean, is it possible to kind of go into more detail about?
Well, we tried to use attention in communication system, not in choose. When we choose, we tried to use attention. Well, we used attention when we extract features, and when we trying to add it to communication, but it seems like communication works better without it. So for feature extraction, we use like some kind of recursive networks, which well, we have tree observation, and then we trying to combine features for each edge into one vector, and well, we do it with multi-head attention.
So, because you said earlier as well that you did you say you had a recursive approach to the tree view?
Yeah.
And so, what do you mean? You kind of walked down the tree view with the neural network? Did the neural network take a single observation of the whole tree, or it's looking at every node in the tree?
Well, it not looking at how to describe it correctly. Well, we have features for each for different edges. Then we transform them with some simple dense network, and then we trying to combine them into single vector with this embedding size, this corresponding embedding size. Like we have 3 edges and trying to combine to vector of embedding size that, well, the same size that we use for embedding features of the edge. This is embedding for subtree, so we embed then leaves of the tree, then we embed their parents, and well, finally we came to the root of the tree with some embedding vector.
So does that mean you're sort of like walking from the root of the tree to each leaf?
No. It's from down to top. So we basically firstly combine this compute features for this subtree, then we compute for top node.
So it's just kind of 3 layers. Was it kind of a fixed? What depth was your tree?
In final solution, if I remember correctly, it's like depths of 2. We tried depths of 3 and depths of 3 and depths of 2, and I don't remember which is better. Yeah. So well, here we have a common problem, like with RNN network, with RNNs. So maybe we should use something more similar to GRU or LSTM, but well, linear layers is fine. We also tried to just linearly process features from each edges, from every edge, just not use this recursive approach, but we find that for validation, our approach is slightly better.
I mean, Nilabha or Florian or Christian, I mean, I think you did most of the work with our sort of baselines. I think that did we experiment with different networks in our baselines, or did we just use different RL algorithms? Like, did we try plugging in any of these different mechanisms? I'm thinking about, because on our side, on the AI crowd side, I don't.
Nope, we starting mostly from scratch, like just, well, we look at your code to understand how to interact with environment, but most of our code is written from scratch.
Yeah. I mean, sorry, Florian, do you know, did we experiment with different networks, or were they all just sort of simple MLPs?
I think for the most part, we didn't do much of that. Most of them were MLPs. I don't think we got a very good solution working on CNN either, right? I mean, apart from the global density, but it wasn't as good as the others. So
I think because so far we've only tried the CNN applied to the global observation. I'm not sure. I don't think we really had a way of applying something like a CNN to our tree view.
No,
we didn't get much success with that. And with global observation, it didn't pan out so well.
Yeah.
But so we did some like systematic test on the DQN baseline with different like depths and widths of neural networks, so still basic fully connected layers. And here it didn't show like much more performance with like larger or wider networks. But yeah, the thing is, for the RLE baselines, there were just too many parameters to search to do this kind of systematic evaluation. So this is something that would be worth doing, especially with like the CCPPO baseline, which is a transformer. Maybe here we could get some improvements. But yeah, no, this is not something we've explored more.
I also generally wanted to ask, I mean, a lot of interesting solutions have come up. So how does people go about trying to debug their solution? I think maybe we've got a new visualization tool, but how did in general the participants figure out, or is it mostly trial and error, or do you have something that helps you debug?
Oleg has been interacting very well, but I would really nudge other participants to also come in. Evgenia, Igor, if you guys would like to, take up this question or just interact in general. We have about 13 minutes left, now 12. So anyway, we're going to kill the call soon.
Okay, I can pitch in. So we spent many hours debugging our solution. It is really hard to do with many trains, especially when the algorithms work on a smaller environment. And then when, I don't know, 20 or more trains come in, it's a total mess. Everybody gets deadlocked. And we didn't do anything smart. We just printed the observation at each timestamp and looked if we have bugs in our deadlock and priority computations, but we would really benefit from this visualization tool. So good job on that, and I hope that we can use it in the other rounds.
Florian, this might be time to announce the next iteration of the Flatland challenge.
Yeah, so first to address the last point, yeah, we really want to basically, as part of the evaluation, as now there are some videos which are generated, also generate the PKL file containing a recording of some of the evaluation and allow participants to download them. And so then they could upload it to the tool that Shivam made. So you could see basically what happened precisely during live evaluations. So obviously, we cannot do that for everything since we need to keep most of the environment secret. But this is an integration that we definitely want to do in the future. For the next competition, so the plan is basically that we will apply next year again to have a new NeurIPS competition. So this will be the second half of 2021. But we're also planning to run a separate competition in the first half. This should be tied to the AMLD conference in Lausanne. So I will leave Moenti to give the precise details during the competition track in a few hours. But yes, this is basically the gist of it, that for now these competitions have been kind of discrete events, but we want to build more of a benchmark around Flatland to have some continuously running round basically, and so basically establish a live benchmark, as you would have the ImageNet benchmark, where anyone who comes up with a new idea can immediately submit it and see how it influences the state of the art, like at any point in time, basically. And so one of the big questions that we have around this is what will be the problem formulation for this long-running round, right? So we introduced this notion of infinite wave for round 2, which kind of put two different pressure on the submissions. First, that they need to, well, the paths need to be efficient, but the solution also need to be optimized. And this is something that I would be really interested to get feedback about. If you think that, yeah, basically how it yeah, how it changed your approach to the problem, and if you think this is a good way going forward to benchmark solutions, or if you maybe have some other idea what would be better settings.
In my opinion, the changes made in the second round were really good, because in the first round we have troubles with the time limit with our reinforcement learning solution. So even it performed actually well on smaller environment, we couldn't evaluate it because it crashed the 8-hour limit. So whatever you do, go in this direction with the infinite number of environments and also 8-hour time limit. It has been a great improvement.
Oleg, did you have the same feeling about it, that the round 2 formulation was better than round 1?
Well, yeah, I think this is better because, well, it is shows more progress of the agent. Like it's allows us to test the sample efficiency of our agent, not sample efficiency, just efficiency in terms of time that it consumes to evaluate our solution. And also it is well, scores our agent for different situations, like for both small and large environments. And well, we figured out that for large environments our agents perform worse than for a smaller ones. So yeah, I think this is better. Maybe you can make well, I think this is good decision to do this scoring, this test procedure in second round. Yeah.
Okay, cool. I see Shivam is asking about more complexity, so different speed for the different trains and having intermediate stops. So actually, the speed profile is already something that we have. I think it was actually used in the previous competition, and we wanted to keep things simpler this year. So it was basically all the trains at the speed of 1. And the notion of intermediate stop is something that we've discussed many times on it's something that would make Flatland closer to the real life setting. I mean, this is something where I guess Eric and Adrian can talk more on this topic. If they hear me.
Or can you repeat? I was away from keyboard quickly.
Yeah, I'm just so the question is about trains having intermediate stops, basically.
Yeah, and this is something we should really try to implement. I don't know if we'll be managed to do this beginning of next year's, but the latest for the next NeurIPS challenge, I think more realistic train schedules closer to what we use in real life should be something we should add. I mean, that will boost complexity vastly, but might be very interesting to solve.
For me, it's exactly the same. I think it's at the moment it's not so realistic, the system. So any agent can start, and what you can do, you can say, okay, well, we start from one location, all trains, and they just spread, and then they reach somewhere else their targets, and then we start again another destination. Maybe we can also include a schedule, and we bring them all functions and said, okay, you have to reschedule as good as you can. And this will also be a very interesting use case. But fortunately, most of the solution I reviewed, the agent start spread, so they stop anywhere. And they think that part of them didn't implement so so bad heuristics. But I think once you have a schedule and you bring in more function and you say you just need to reschedule, then become become a real world application out of the results. This can also be a next step in Flatland.
Yeah, and maybe you can add some like time windows in which trains should arrive at the specific point.
Yeah, that means we need a schedule generator, and then we can provide a earliest departure time and latest arrival time for each train, and then you should find solutions in this time window. That's a great idea. And it's exactly what we try to solve in our company in the SPV.
I have a sorry, who I interrupt.
Go ahead.
I have a question for Oleg. You mentioned in the video, but can you repeat what was your reward structure? Because we struggled with it a lot. If we define just the main goals, that means positive reward for getting to the station and negative rewards for deadlock. The agent have had really troubles to get to the station and get these positive rewards, so they just stayed and didn't exit stations. And if we included some sub goals into the reward structure, then the agents often learned to exploit that. For example, we gave a positive reward for avoiding deadlock, and they deliberately get into these avoiding deadlock situations so they can exploit that and get this positive reward that we were giving. So again, to the base question, what was your reward structure?
Well, our reward was quite simple. We just reward our agent with 10 points if it succeed, like arrived to the destination point. We punish it for 5 points if it's deadlocked. And we also had a small reward for coming closer to its target. Like 0.01 or something like that for each frame it comes closer. Well, it seems like we additionally use some well, we try to detect all possible deadlocks, like not when the trains just standing close and just faced each other, but also situation when they can't do anything to avoid this deadlock.
Okay, thanks.
I have a question to the participants. Maybe I saw your presentation was very nice. And also, how do you handle exactly this problem that Oleg now mentioned? I mean, in Flatland, the decisions you take at one point will lead to bad behavior in the future, right? So kind of mapping your action to the correct observations. Also, Jeremy mentioned this in his task. If you take an action, then your observation changes, but then the negative reward and the according observation is way later. So you have many like dummy observations in between where nothing happens. You just travel around the track. How did you manage to overcome the difficulty of the large time between your action taken and the bad thing happening?
Well, it's an interesting question because for small environments, people just managed to solve this problem on its own. But when we try to scale this our solution as is for larger environments, it surprisingly trains worse. So that it's just like showed worse performance even on this scale environments, larger environments, than agent trained on small environments. So we basically do not know how to deal with large environments yet, and people is not helping in this problem because it's stochastic, and for large environments, it's well, dramatically leads to critical situations when agents makes wrong decisions.
Thanks. I might have some another question into the groups. Early on, so I work at SBB, and I'm one of the co-creators also of this Flatland environment. And early on, we started looking out to graph neural networks as well to kind of help, since it's a graph structure on the problem. Did any of you guys investigate graph neural networks to either extract features or help in decision making?
For us, it's future work.
We didn't either, so that's a good idea for the next round.
How about you, Jeremy, as well? I really liked your presentation, and I was wondering, like you computed the probabilities of each path, right? This could also, maybe you could use graph neural networks to kind of estimate the probability of which path an agent will take, right?
Yeah, I mean, that was the kind of the intention of this thing. And I mean, you know, so far I haven't got to the stage of really being able to plug a useful RL agent into it. It's because it has this kind of probability thing that's differentiable. It was, in a way, it sort of solves itself, you know, given the paths that it sort of starts with. And so that's why I'm really trying to understand how we can sort of, you know, feed the right information into an agent to so, you know, present enough information for an agent to make the right decisions. And so far, I've been focusing more on paths than the graph. You know, so the paths are kind of sort of once a path is created, then it doesn't, you know, there's not really much more that it does to it. It just kind of introduces pauses. So because I you know, personally, I still don't really, I've, you know, tried to read a few of those GNN papers, and now I'm struggling to really understand how to fit it in, you know. we're all hoping for a way of doing it. But because in a way, it's like, you know, for Flatland, are we really solving a graph problem, or are we just solving a kind of a scheduling problem of just, you know, weighting, you know, pick a combination of paths? It seems to be, you know, at the moment, in terms of my own understanding, it's kind of a question of combining paths and pauses, and the sort of navigation aspect. Because I think the GNN examples that you find in papers are things like what is it? You know, traveling salesman type problems. I haven't really seen a multi-agent GNN. Maybe someone else has, but, you know, there's a lot of kind of single, you know, find the shortest path, or those, you know, variations of traveling salesman problem. Anyone else seen a multi-agent GNN? No. I mean, it sounds promising, doesn't it? You know, so yeah, I mean, the probability thing, actually, for what it's worth, with those probabilities, it seems to kind of, the probabilities move from kind of like kind of initialize them all as roughly equal, but with a bit of randomness, and then they very quickly kind of move to like, one of them gets probability 1 and everything else gets probability 0. You know, if a path has a, and I think in a way I must be missing something about what it's actually doing. It's you know, it's probably just, you know, in effect, what is it doing? It's kind of counting the number of conflicts, and the path that has the least number of conflicts kind of gets pushed up. Everything else gets pushed down. So very quickly comes to a sort of a local minimum. But I kind of think that the, you know, the answer must be something to do with you know, a slightly more intelligent way of creating, of modifying paths and creating new ones. You know, how do you give it enough information? So things like the background information of things like alternative paths, and you know, what's the like the I think was it Christian showed us those wonderful sort of density plots, and so in effect mine would, I think, you know, if you kind of have an alternative path and then kind of plot the density along a given path. So in other words, you can kind of keep the observation the same shape. The observation is just really, you know, more of a vector rather than two-dimensional. And so the additional rows would be things like alternative paths stacked alongside each other. That's kind of my current thinking.
Well, it can be handled by something like convolutional neural networks, maybe.
Exactly. That's kind of what I think is like, if we can stack the right information alongside, so you've got kind of contiguity, or like you've got kind of relevant information next to each other. I mean, the problem with the staircase diagram thing is because every time you've got a junction, you kind of basically got to jump. It's no longer connected. And if you remember that diagram where it's taken an alternative path, and the alternative, you know, the main path is up here and the alternative path is kind of down here, and there's a jump. And so as far as I can see, that's going to break a CNN, because if a CNN has got a little window that's scanning across this you know, the staircase diagram, it's only really looking for local features. So I don't know if there's some way of either tricking that thing to to have a different topology so that it can see, you know, that something's really adjacent when it's not in the diagram. I don't know. It just seems like a complicated thing. So that's why I kind of think that, you know, some sort of an observation that's consists of different paths, you know, stacked alongside different paths, or maybe different sorts of information about the path, and then something like a CNN might be able to make some sense of it. That's what, again, as I say, that's what I'm hoping.
There are some papers like stepwise attention where they are trying to use discrete values, but in which we can backpropagate gradients. So it's not exactly what you look for, but maybe it's somehow connected.
Stepwise attention.
Yeah.
Yeah. Yeah. Yes, as you say, I mean, essentially, when I sort of refer to the sequence-oriented networks, I guess, you know, I think attention it comes from sort of NLP, doesn't it? So it's something that's processing a sequence.
Oh, well,
is that right?
This attention actually comes from speech. So as improving of Tachytron model, and well, I'm not suggesting you to use a whole attention mechanism, but to just look into an idea how they embed discrete variables, discrete outputs of network.
And that's in terms of like kind of encoding the action, or we say that you've got discrete variables coming from as an output of the network. Are you thinking of the action there?
Yeah, like well, we want to move some some part of the path to the another road, or if I remember correctly.
Yes, yeah, exactly. Yes,
so
manipulate. Yeah,
maybe, and this may be considered as like stepwise attention if we want just well stay in this part of the road or move to another in each switch.
So what you think in terms of like using it to make navigation choices?
Maybe yes.
Yeah. Yeah. Yeah.
Okay, we are running out of time. The NeurIPS talk will start again. Things have restarted again actually just now. So yes, the competition track will start in about 1 hour, where there will be more announcements about the new competition. There will also be the official announcements of the winners, even though we've kind of spoiled some part of it already. Yes, so hopefully we can do this again in person in a real room at NeurIPS next year instead of a virtual room. And Laurent has shared the social media information of AI Crowd on different platforms, so you can follow us there for to get more information, and notably the recording of this video with all the different talks will be released publicly soon, and we will announce it on these different channels.
You know, we didn't realize it. It ended up being more than 2 hours, and it's still running. You know, in order for us to close, I would really nudge everyone to, for one last time, switch on your videos. So we take one selfie, and then we close it. It's a kind of digital Zoom selfie. If others, if they would like to switch on their videos. Okay, it seems it's going to be about it. I'll take the selfie. Great, one more. Thank you. Thank you all.
So thank you everyone, and see you on the next competition.
Yes, cool. Thank you.
Cheers. Bye.
Thank you.
Thanks, guys.
Thank you.
Bye, guys.
Thank you.
Thank you.
Bye.
Thank you.